Let's talk about trigonometry. I know, for a lot of us, that word probably brings back some less than fond memories of high school math class, right? But the truth is, trigonometry is so much more than just triangles. It's this beautiful, powerful language that describes the rhythm of pretty much everything around us. And to show you what I mean, let's just jump right in with a question.
So, a musical note, the AC current in your house, the ebb and flow of the ocean tides, what on earth could they possibly have in common? Well, they all move in cycles. They're all waves. And the hidden math that connects all of this stuff, this language of periodic motion, yep, that's trigonometry. It goes way, way beyond just measuring triangles.
So let's start where most of us did, in the comfortable, predictable world of the right-angled triangle. It's actually a great place to begin, but as you're about to see, it's really just the launching pad for a much bigger, much more interesting journey.
I'm sure you remember this guy, SOHCAHTOA. It's a neat little mnemonic for how sine, cosine, and tangent are defined. They're just simple ratios between the side lengths of a right triangle. You know, for any specific angle, the ratio of the opposite side to the hypotenuse is always the same, and we just give that ratio a name, sine. It's simple, it's elegant, and it's super useful for triangles. But here's the catch. This whole definition hits a wall, and it hits it hard. I mean, the angles inside a right-angled triangle have to add up, right? You can't have an angle bigger than 90 degrees. So what happens when you want to describe something that rotates 180 degrees, or 360, or even goes in a negative direction? Our triangle-based system just breaks. We need a bigger idea, a better one. So let's completely shift our perspective. Let's build a new tool, a kind of machine, that can handle literally any angle you can throw at it. This right here is where trigonometry really opens up and gets interesting. And this is our machine, the unit circle. It's so simple, it's brilliant. It's just a perfect circle, plopped down on a graph, with a radius of exactly 1. That's it. This one simple shape is the key to unlocking everything else. Okay, first, we need a slight upgrade in how we measure angles. Forget 360 degrees for a minute. We're going to use something called radians. And a radian is just a measure of distance, the distance you travel along the edge of our unit circle. Think about it. The circumference of any circle is 2 pi times the radius. Well, our radius is just 1, so a full trip around the circle is a distance of exactly 2 pi. Simple as that. Now, I absolutely love this quote from our source material because it creates such a perfect mental image. Just picture the number line, 1, 2, 3, all the way to infinity, and imagine literally wrapping it around the circle like a string. Every single number you can think of, positive or negative, now lands on a very specific point on that circle. An angle of, say, 5 pi over 2? No problem. That's just one full wrap around the circle plus another quarter turn.
And this slide lays out the new rules of the game. It's a really simple process. Step 1, pick any number you want. That's your angle in radians. Step 2, travel that exact distance along the circle's edge. And then, step 3, just look at where you ended up. The x-coordinate of that point, that is the cosine. And the y-coordinate, that is the sine. That's the whole definition. And it works for any angle, no matter how big or small. We're totally free from the limits of triangles now.
Now, because we have this powerful new definition, something absolutely amazing happens. For the first time, we can actually draw a picture of what these functions really look like as the angle just keeps on going.
So let's focus on the sine function. And remember, that's just the y-coordinate of our point as it moves around the circle. When we start at an angle of 0 radians, our point is sitting at the coordinates 1, 0, so its y value is 0. That means the sine of 0 is 0, and that's the first point on our graph. Okay, now watch. As we start moving around the circle towards pi over 2 radians, that's 90 degrees, our point climbs straight up. It goes higher and higher until it reaches the very top of the circle, at coordinate 0, 1. The y-coordinate has smoothly risen to its maximum possible value, 1. And look, you can see the first peak of our wave starting to form.
But we keep going. As we travel from pi over 2 pi radians, or 180 degrees, our point sweeps down the other side. The y-coordinate starts to fall, smoothly decreasing from 1 all the way back down to 0. And just like that, our wave has crossed the center line. Now for the second half of the trip.
From pi all the way around to 2 pi, our point dips below the x-axis. The y-coordinate becomes negative, hitting its lowest point of -1 at 3 pi over 2, before rising back up to 0 as we complete the full circle. And there you have it, one perfect, complete cycle of a sine wave. And this is where the real magic of the unit circle becomes clear. Because we don't have to stop, we can just keep wrapping that number line around and around and around forever. And every time we do, that pattern of y values will just repeat itself over and over again. This repeating nature is called periodicity, and it is the single most important feature of a wave.
So here's the key takeaway. The period of a basic sine or cosine wave is 2 pi. What that means is the entire shape, the whole up and down pattern, repeats itself every time we travel a distance of 2 pi, which, of course, is one full trip around our unit circle machine.
So now that we have these two fundamental waves, sine and cosine, the real fun begins. We can start to play with them, to manipulate them. We can learn to speak the language of waves and use it to describe basically any cycle you can imagine. For example, what happens if we just multiply our whole sine function by a number, let's say 2? Well, every single y value just gets doubled. The wave still has the exact same rhythm, the same back and forth, but it's been stretched vertically. It now bounces between -2 and 2 instead of -1 and 1. We call this property the amplitude. It's literally like turning up the volume on a sound wave. The sound gets louder, but the musical note stays the same.
Okay, but what if we multiply the angle inside the function, like cos 2x? Well, now we're telling our point to travel around the circle twice as fast. This means it completes a full cycle in half the time. The wave gets squeezed horizontally. Its period is now just pi instead of 2 pi. To go back to our sound analogy, this is like playing a higher note. The frequency has gone up.
So let's just pull this all together. The big idea is this. Trigonometry isn't really about triangles. That's just where it starts. At its heart, it's the mathematical language of cycles, of rotation, of waves. And these two functions, sine and cosine, which are born from the simple act of spinning around a circle, are the fundamental building blocks for describing pretty much everything that repeats in our universe.
And that leaves us with one final, really cool question. We've seen how to build the simplest, purest waves possible. But the world around us, the sound of a violin, a Wi-Fi signal, the weather, these are all incredibly complex waves. So what happens when you start adding these simple sine and cosine building blocks together in different combinations? What kind of amazing complexity can you build? Well, that's a story for another time. Thanks for watching.